Okay, can you see the screen with the homework?
Yes.
Yes.
Okay, so, but anyway, so first problem, no problem, basic problem, you can figure it out. But the second one is I want you guys to have some experience implementing particle filters. So technically this problem is linear dynamics and linear observation. So you technically can do it with common filters, and I asked you to try to use common filters as well. I don't see why this problem is because everything's linear, you can also use common filters, but you should try to use particle filters as well. But just to explain the problem, because just the setup is kind of strange. So the idea is that you're going to track this little robot moving in a room. So what you have is, imagine that you have the view of a camera on top of the ceiling. So it's actually looking down on the little robot, right? So from that perspective, the little robot just looks like a little square. So it's a 5x5 pixel red square. So it's going to move in this room, and the room is a 300 by 300 pixel square. So I'll show you what a picture looks like. Okay, I'm just gonna share desktops. Okay, can you see my entire desktop?
Yes.
Okay, so just to make clear what the picture, so the picture looks like this. So you see, it's like the square is the room, this little red dot is the robot, right? So you kind of zoomed out. So, but this room has these rafters on the ceiling. So, or there's something there that's occluding, that's the black bar. So the robot is going to move in the room. I mean, this is all generated data, right? So this is all, I have to this is not like from a real camera. But anyway, the robot is going to move in a weird path, not a straight line. I mean, it's a weird curve. And it's going to move until when it passes through the black bar, you won't be able to see the robot anymore, right? So it's going to move from frame 5 to frame 6, and then it's going to pass through the black bar. So that's when you kind of lose sight of the robot. So the idea is and then after a moment, it's going to come out of the little black bar, and then you'll keep resuming in its own path. So the goal of the project is to track the location of this little robot, right? So again, the reason is because it's generated data. I actually know the true state of the red dot, and you can compare then your tracked state compared to the true state. So that's that. Right. So the state of the system is going to be a 4-dimension vector. So first you have the x location, the y location, and then the velocity in the x direction and the velocity in the y direction, right? So the dynamic is very simple. So you have this update dynamic model, right? It's linear, and you can figure out what the A matrix should be. But the dynamic, of course, also has dynamic noise associated with it, and I give you the mean and the covariance. So when instead of having to do image processing, what I did was I extracted for you the measurement you will get associated with each of these frames. So ideally, in practice, in the real world, what you have to do is, on top of filtering, you actually have to do image processing to try to get measurements from your picture, right? So it's not too bad here. You just go look for pixels, which is color red. But I did that for you. So every frame, you get a measurement, and the measurement is also going to be 4-dimension. It's going to be the location, the XY coordinate of this dot, and also the estimated or the computed velocity. So the computed velocity of measurement is just going to be the location at current time minus the location at the previous time divided by time, which in this case is 1. So that's how we compute the measured velocity, right? So the tricky thing is, of course, when I get to a frame where the little robot is occluded from view, my measurement is going to go I can't find this little thing, basically at that point the measurement you don't have, right? So when at that point the measurement is going to default to some set value, but basically what makes this an interesting tracking problem is the fact that occasionally you're not going to get any good measurements from the robot because it's not going to be in view. But similarly, the measurement follows, it's actually very simple in this case. The measurement at time t is just a state, since the measurement is exactly the state. So the state at time t plus your measurement noise, right? So I also give you the mean and the covariance noise of the measurement noise. So the idea is to basically use particle filters to track the state of this little robot. So there's some questions to help you get started. I tell you, you should try 100 particles and see if that works well. You could try like having more or less particles, but 100 is probably a good rule of thumb. You should have I give you the initial state. So you don't have to play with image processing at all. So what I do is I give you the measurement, right? In each frame, I give you a measurement. So for the frame where the little red dot is not in view, it defaults back to the x coordinate 1 and the y coordinate 1. And then the velocity goes crazy because now you have some reset. The coordinate no longer makes sense. But basically, every so often, you get good measurements, and then you get bad measurements because the little robot is not in view. And also to make your life easy, I also give you a thing which tells you which of the measurement is good. So if it's 1, that means the measurement is good because we can see the little dot. If it's 0, it means we cannot see the little dot, so you should not trust the measurement. So you can either use this flag to tell you when the measurement is good and when the measurement is bad, or you could do basically go look for the case where the XY coordinate is 1, 1, like really different from the previous measurement. So that's your observation Y, right? So basically the idea is that we're supposed to create, the particles, the trajectories, and the way we weight the trajectories. So you should implement the simple bootstrap sampling resampling algorithm, right? So in that case, you need to implement resampling as well, but also you know that your importance distribution is the simplest one we can use. It's not the optimal. It's the one where we just use the state transition probabilities. So you need to figure out what that thing is first. And you also need to figure out the likelihood, because when this is the importance function, the likelihood is the weight is the likelihood. But because when you cannot get a good measurement, you should not use the likelihood as the weight, because the good measurement is no longer there. So what you should do is, just think about the problem, and then think about if you don't have access to a good measurement, right? If the little dot is occluded by the black bar, first of all, what can you use? What should you use instead for the measurement? And also, because it's basically a blind guess at that point for every single trajectory, since we cannot get the actual measurement at that time, the normalized weight for all the trajectory should be the same. So it should be 1 divided by the total number of particles, right? So as opposed to, usually we will weight the trajectory by the likelihood, but when we can't actually get any good measurement, we can't weigh it by the likelihood. Instead, we just give everyone the same normalized weight. So when you implement it, what you do is you generate the trajectory for all 150 frames. You estimate the state of the particle for all 150 frames, and then I give you a .m file to which has some plots of what is the mean square error, the measurement error, and then just a visualization of what it looks like when you have the actual particle, the measurement and then your tracked observation. So that way you can visualize it. Then the other thing is, so suppose we don't see this picture. If we only get the measurement, then how can we use this measurement to try to figure out where the occlusion is, right? So imagine you want to figure out what the ceiling beams are. So if you don't see this picture, you just see these measurements, then try to figure out a way to figure out what the ceiling beams are. And then the last thing is, since this is a linear system, really, you can try using Kalman filters and see if that does better or worse compared to the particle filters and performance-wise, and also in terms of computation. So I think this should be, it's about as, it's somewhat realistic. I mean, in the real world, you probably won't get a room this clean, but it's kind of like what people use particle filters for when it comes to tracking the movement of this little robot. Yeah, so there's only 2 problems in the homework. So yeah, so give this a try. Let me know if you get stuck. But the idea is that, you know, some of these questions are meant to lead you to try to figure out how to implement this. So if you really have no idea how to answer some of them, that probably means that you need to figure out the solution to, say, the first part A through D first, before you try to just write your code, right? Yeah, okay, so any questions? Oh, and also I included true, when we compare, we don't compare velocity, we just compare the estimated location of the robot with the true location of the robot. So I've included that as well. Okay, so any questions? I can't hear anyone.
I don't have any.
No questions yet.
Okay, but the task is clear, right? Like what the measurement means. So basically, I uploaded these files in Laulima. So at least be clear on what each of these files give you, right?
Yeah.
Okay. Why did some people have this little X circle next to their name? I don't understand.
It's just like a thing. This basically says no for the thing.
Oh, like you guys accidentally pressed no for something. Okay.
Yeah.
Basically like.
Oh, that's supposed to be the response. Okay, I see. I'm supposed to look at that instead of you saying something. Okay, yeah, that's gonna be difficult for me. I can't look at things, write, and talk at the same time.
Yeah.
Okay, so then we'll keep going. So today we'll finish up particle filters. So hopefully you guys get with the code, you get a way to see how it's used. So again, it's and I'll talk about like a real world example, but you see that it requires, it's like even like this, right? Even for the simple tracking problem, I mean, it technically also does include computer vision. So it's not just, you know, I'm done. I know particle filters, I can solve all problems. You do really need some expert domain knowledge. So this is like a very simple computer vision type problem. Okay, so let's see. Okay, so we'll finish up where we left off on Monday, right? Which is so for this example, you're going to, for the homework 4, you're using the very simple importance distribution to generate your particle, right? Right, and so that's called the bootstrap So what we really need is, in general, we need this importance distribution, which is the probability of the particle at time n, given all the past histories of its state and then all the past observations. But in the simplest one, the bootstrap, this is going to be just the transition probability. So the particle at time n given the state of the particle at time n minus 1. And then on Monday, what we talked about was that there is a better choice, that this is simple, but in theory, in practice, the worst choice, worst performing choice. And in the best one is what is called the optimal importance distribution, or the optimal importance function. Right. And so what that is instead of the importance distribution being this, so now the importance distribution should be something that takes into account also of the current observation. Right. So this is the optimal importance function. So the downside to this is you may not know what this is, because you have a very complicated dynamic and very complicated measurement models. You may not know, or you may not know this in closed form. It may be very difficult to generate samples from. Meaning that, you know, this is not a Gaussian or exponential or Poisson. It's not a standard distribution that we know how to generate samples from. So for all those reasons, people still, I mean, you will, like, people do use the very, very simple bootstrap sequential sampling. And most of the time, I mean, sometimes it's good enough, but this is, in theory, the optimal, but in practice, it may be difficult to use. So on Monday, we said that there was a case when this is known, when the optimal importance distribution is known in closed form. So there are cases where this is useful, and if it's known in closed form, you should use this and not the simple importance distribution. And in that case, the case where this is known in closed form, it's the case when you have a nonlinear dynamic but a linear observation or a linear measurement model. So the nonlinear dynamic is x to time n, is some nonlinear function g, taking in the state x to time n minus 1, plus the dynamic noise, which is assumed to be Gaussian with some covariance matrix, and the linear observation model it's some matrix times the current state plus your measurement noise. Right. And then we said, well, the way we can find the closed form distribution, the optimal importance function, is we can use Bayes' rule. So the probability of x at time n for the ith trajectory, given the state at time n minus 1, and the observation at time n, if we do Bayes rule plus, you know, Bayes rule plus manipulation, what we can do is we can see that this is, we can divide this into the likelihood times the transition probability divided by the conditional distribution. So again, this is, it's not, you can't just apply Bayes rule here and get this form. You do have to do Bayes rule plus some additional manipulation and you get this form. But what this tells us is that if we use the optimal importance function, the normalized weight update equation, right, it's going to be the old normalized weight times this incremental correction factor. So in the simplest kind, in the simplest importance, in the simplest particle filter, this term is just a likelihood function. But if we were to use this optimal importance function, then this term becomes not the likelihood, but this conditional probability, right? So this analysis is in the notes. So basically, if you were to choose the optimal importance function as the importance distribution to generate your sample from, then this is your incremental factor. This is what you're going to multiply the previous weight by in order to update your weights. And then the way we argued is that if you have this model, right, then like we did the analysis here, the likelihood becomes a Gaussian. The transition distribution is a Gaussian. So the goal is, the idea is that basically with analysis, what you can show is that this thing, the optimal importance distribution, is also a Gaussian. But it's a Gaussian with a fairly complicated closed form solution. So I'm not going to go through the exact details here, it's in the notes. But basically, this thing is going to be Gaussian with mean this mean is this term, which is, I'll define what sigma is in a moment. So sigma n times the covariance matrix of the measurement noise inverse right. So this thing is the measurement at time n, the covariance of the measurement noise, the matrix H from the linear measurement model, the function G from the nonlinear dynamics model, the inverse of the covariance matrix of the dynamics noise times this sigma n. And this sigma n inverse is the inverse of the measurement, the dynamics noise, the covariance matrix of the dynamics noise times the inverse of the covariance matrix of the measurement noise. And then again, the linear function of the measurement. So none of these terms are super I mean, they all appear in how we specify the state space model, except they're, again, it's not this one line derivation from Gaussian, but all of these terms appears because this is a Gaussian, this is a Gaussian, this is a Gaussian of some sort. So then this entire thing ends up being a Gaussian. But the mean of this Gaussian has to be, it's dependent on the mean of all of these three. So that's why it appears a little bit more complicated. Right. And then and this is also, this term is also the inverse covariance matrix. Of this. So this thing, the covariance matrix, but the inverse of the covariance matrix is also this. So basically, if we have a simple model, if we have a model which is only nonlinear in the dynamics model, then we can use the optimal importance function. And we know we can generate samples from that because it's a Gaussian. You just have to be careful specifying what is the mean and the covariance of that Gaussian. Okay, so what is other than these toy problems where I generate data, what's a more realistic type of scenario that you can use this? So one thing is particle filters is used for ballistic target tracking. So again, it's like the homework with the little dots, except this is a little bit more complicated. You're now working with a toy problem, which is generated on the computer. But what you want to do is you want to track a ballistic target entering the atmosphere at hypersonic velocity, right? So you can imagine that the measurement you will get from this via radar or whatever is probably very, very noisy because it's moving very, very fast. And due to the dynamic of the atmosphere, due to the makeup, right, you have all sorts of materials in terms of air density and all that. So due to the atmosphere, this is not like a straight, the orientation of this thing is going to be perturbed, right? So because you have a lot of thermodynamics and fluid dynamics in there that will change the trajectory of this thing. Okay, but the system, see, this is why I changed the notation in the book. So the system is the same actually as with the little robot tracking. So you would track the X and Y coordinates at time n, right? So that's why instead of X, I used S in the homework. And then you will track the velocity in the X direction and the Y direction. So can you guys guess why I don't have the Z? Because this thing is technically, we know the real world is 3D, right? So this thing is coming into my atmosphere. How come I don't have Z? Any guesses?
If you kind of almost say normalize the trajectory, and also assume the missile's like coming straight at whatever the observation target is, or at least almost like assuming no Z variation and just call the Z plane whatever, I guess would be the Z plane, but call it just kind of like say, hey, it's moving in this flat plane. So the only measurement I'm going to observe is it moving laterally or in my field of view or how fast it's coming towards me?
So if sorry, so if this is me house and this thing is coming toward me, I think I will want to know what the z trajectory is because I want to know if it's here or if it's here, right?
If you call that like X and Y, or call that X, and then know whether it's gonna hit next to you or side to you Y.
Yeah, but okay, but rather than the very tricky thing of reorient my direction of X, Y, and Z, instead of doing this, if I switch Z here and Y there, yeah, other than, but suppose you don't have to rechange your coordinate system. I guess what I'm saying is, this is probably not the scenario where you would disregard Z, right? Because Z will be very important if the scenario is this thing is coming right at me from the sky. But you're right in the sense that, of course, if I don't have Z, I'm assuming that this thing is actually moving in a 2D plane. So it's not the scenario, I think you can see that it's not reasonable for this to be the scenario where the thing is coming down at you, but this is possibly the scenario where the thing is, here's you, this thing is flying above you, right? In which case, if it's like, God, I'm not good with height. I don't know, 30,000 meters above me, or 35,000 meters above me, and maybe it doesn't make that big of a difference, right? So that's what I meant. It's like, if it's coming right at you from the sky, you definitely care about what Z is. But in the sense that if it's flying ahead of, on top of me, like with planes or whatever, or when it first enters the atmosphere, it's probably, or it's probably too high above me for me to care about what the Z is. Right? So, but my point is, these are not things where you can blindly apply to computer science. You do, if you, to work on this, even the consideration of what is the state requires understanding the application. Right. So maybe if I care about this thing falling down on me, I would change the state to something else of things I care about. Okay, so then you have the state. Then you also have to understand, well, how is my state changing in time? And that is not, at least I don't understand where these equations come from. Somebody in physics or aerodynamics understands. But this is just to show you that in many of these applications, this dynamics model, it's very domain specific, right? We work with for toy problems, we can work with a very simple model, but for these sort of more realistic scenarios, you want to work with something more complicated. So G here is the gravity constant, gravity acceleration constant. I don't remember what that is. I remember it from physics once in a while. I mean, I had to memorize for class, but I don't remember it now. Okay, and then you assume your measurement is taken delta t time apart. So then F, this is your very basic dynamic of the position in the x coordinate is current position plus velocity times time, right? So that's where these equations come from. Then G here is, so this little f function has to do with the aerodynamic drag force. So again, some nonlinear equation involving some constants. So the third element of the state, square root of right. So this is obviously, is this thing makes it nonlinear, right? Because this is not a linear function of x. So basically, bunch of terms, bunch of equations, you still have your standard Gaussian noise, but other than that, it's a nonlinear equation. And then in observation, this one is more complicated because I'm now going to be able to observe most of the state. The observation comes from a radar. And radars don't measure the XY coordinate. What it measures is the range. So how far apart this thing is from me, and also the angle, the elevation angle. So that's why it's also a nonlinear function of the state, right? So range and then the angle. And then plus measurement noise. Right. Okay, so basically this is a more realistic real world scenario. But again, to us to work on this, you need to understand, there's a lot more physics background and then also understanding radars. And I'm sure this is only like a toy model of what the type of noise that you will get in terms of radar measurements, right? So here is just the distance and then here's just the angle. But you can imagine how noisy these things are in real life. But anyway, but this is what people use particle filters on. So in fact, this you can do calculus, right? Because a lot of these are dynamics equations. So you can actually do calculus and come up with a local linear approximation, right? So like what we did for the extended Kalman filters, a lot of these nonlinear methods is basically to find a local linear approximation of your nonlinear equation centered at some point of interest. So here, what you can do is you know what the state, or you can estimate what the state is at time n, and then around that particular at that particular state, you can linearize this equation at that point. And then you can turn this from a nonlinear observation model to a linear one. Right. And if you turn this into a linear observation model and you still have a nonlinear dynamic system, then you can use, we know that you can, and all the noise we can assume to be Gaussian, and then you can use the optimal importance function in particle filters, right? So that should give you a better performance than if you were just to use the basic bootstrap particle filters. But there's a combination of having to understand the particular application domain, having these equations, and then use calculus to see if you can perhaps linearize your nonlinear functions around a point, and then you can use particle filters, right? So particle filtering is kind of like the last step of this pre-processing. Okay, so that's all for particle filters. Again, it's not every single problem you can apply to particle filters, but of these sort of tracking problems for robots, for people, they tend to use particle filters on. Okay, so we're done particle filters, and I'll introduce. So one thing about particle filters and Kalman filters is that both this dynamic, the state, and the observation, these are all continuous valued, right? In that, so the state, like say for the little robot tracking, it's well, okay, although that one's not technically okay. So the like say if I'm talking about the XY coordinate, right? I could say that this thing is at 1.25 and 2.78, right? Or if I'm talking about velocity, then I say, well, this thing can have minus 25 or plus 25 miles per hour, right? I can talk about velocity. And then also when I'm doing observation, like elevation angles, it can be 61.258 degrees, right? Or something like that. But you see that whenever we work with Kalman filters and particle filters, the state we're talking about are continuous value numbers, even though it could be a vectors, continuous valued elements. And the observation, we also assume to be continuous valued elements, right? And so therefore, that's why the noise we consider is Gaussian, right? Because the Gaussian is a continuous value random variable. Right. So the elevation, it could be the true measure elevation is 61.258 degrees plus or minus 0.0018 degrees, right? So it's everything is continuous valued. So that said, there are problems out there where I have to deal with the state and observation, which are discrete valued. Right. So discrete valued are like head or tail, high, medium, low, right? And like people, right? Like facial recognition of photos. Right. There's one photo, the photo of the first person, photo of the second person, and so forth, right? You don't get photos of 1.78th person. So there are applications out there which have discrete value states and observations. So when it comes to these sort of applications, we cannot use particle filters or Kalman filters on them at all, because that's not the nature of those sort of models, right? So we have to come up with a different model. So it's going to be similar to a state space model, where we still have things that, like we still have state that evolve in time, state and measurement that evolve in time. The state is still unobserved, right? So again, it could be called unobserved, it could be called hidden, it could be called latent. So it depends on which domain you're talking about. But the state is still unobserved. And so the only thing we know about the state is through these measurements, which are observed. Okay. And our problem is still to, given measurements, most of our problems still has to do with try to estimate the state. Okay. So that's still what most of our problems revolve in. So basically, it's exactly the same as the framework that we've been dealing with in Kalman filters and particle filters, except everything we will deal with now is going to be discrete valued as opposed to a continuous valued thing. So this thing is called a hidden Markov model. So if you have time series involving continuous value things, you look to Kalman filters and particle filters. If you have time series involving discrete measurements, you look to the hidden Markov model. So one thing about this is, okay, so we know that when we talk about state space models, right? We always see these dynamic equations, right? So it could be linear or nonlinear. If it's linear, it makes our life easier. If it's nonlinear, then we have other ways. And we have these noise addition. So if these things are not discrete valued, can I still write my state space with these type of equations? Like,
What's our noise?
you get to pick the noise.
So if the noise is discrete, we could write it like this, right?
Can you? Okay, so I guess one thing is, okay, don't restrict to your basic. I mean, you don't, like, for general function A, right? Like, don't restrict it to the identity. So for general functions, it can be linear or nonlinear, but don't think about this specific case, which then, yes, I think I agree with you. But think about general functions.
When you say that, like, we have a discrete valued, are we like, and you say a general function, does it have to be like an integer output to be a discrete valued?
No.
So it could be like the function could put out whatever and you could still call it discrete, right?
Well, the input, so suppose the input to the function xn can only be 0 or 1, but say an is the sign, actually that's a bad, well, good enough, sign of xn. I mean, that's a general, that's still a function. So you could input a discrete thing, but what is an of xn, the output?
It's gonna be it's gonna be a continuous function. That's
right. So my question, yes. So I'm okay. So my question is, if I'm working with the system where I know the state has to be discrete and the measurements are discrete, can I specify my model like the way we've been doing?
no, you'd have to put additional constraints on it.
Right. So basically, the answer is no. Right, in the sense that it could be very possible that this function is continuous, or this function is continuous. In which case, the state at the next time or the measurement is no longer constrained to be a discrete value, right? So if I only work with discrete value things, it's not natural to write it like this, because this is how we specify how things change when they're a continuous value. But this is not a natural way of specifying a model when it's discrete value, right? So that's the only point. So of course there are cutesy special cases like this, right? Where if this is discrete and this thing is discrete, then yeah, it's like 1 + 4, 1 + 5. I mean, it'll always be discrete, but it's not, in general, it doesn't work like that. This is a very unnatural way of describing a discrete model. So what it turns out then, the only thing I need for a discrete valued model is conditional probabilities. So I can visualize my system like this, right? I have the state in different time, and I know that the state from time 1, from time 2, from time 1 can go to time 2, can go to time 3, and so forth, right? So it need never to end, but it doesn't matter. And at each state, I have some observation. So I don't directly observe the state. The state is hidden, latent, unobservable. I observe the measurement, right? So the simplest model I can assume is this, right? The only thing I need to specify my model is, like with the comment filter, I specify what's the probability of seeing the state at x2 given x1, what's the probability of seeing the state x3 at given x2, and so forth. Right. This is like what we showed in the particle filter. This is your state transition probability. And the only thing I need to know regarding the observations is what's the probability of seeing the observation y1 given x1, right? So this is the likelihood. Right. So that's all I need to really naturally characterize my discrete valued state space, right? I don't need this dynamic because I don't have one anyway, but what I need is these conditional probabilities, right? And obviously the simplest type model I can work with is if all the state transitions, if all of these probabilities are the same, right? I'm not saying for all applications this will make sense, but if all of these things are the same thing, then I don't have to keep in track of what time I'm talking about. I know these are all the same thing. And if all the likelihood probabilities are the same. Right. So this will be the simplest case. But you can, for other applications, this might not be a realistic assumption. Right. So yeah, so this is what a hidden Markov model looks like. You can of course think of your comment filter and your particle filter like this. The only thing is then you know, you can think of it like this, but it's much more natural to think of things like this when it comes to the discrete valued things. Let's see. Okay, so I guess we'll continue on Monday with this. So this thing is called the hidden Markov model. So again, it's like the discrete valued analogy to the comment filter and the particle filter, but the nature of the problem is different. So what this tends to be used for is speech processing. Right, so more of these, and a lot of these computer tasks tend to use this. And the way is, so suppose when when you talk to Alexa, you say a word, so it's really, it's like an audio signal. So the audio signal, they're going to do some pre-processing and break it down into, I don't know, vowels and consonants and so forth, right? So then these breakdowns would be your observation, right? And the goal is, given my observation, what is the hidden state? So is this the word, gosh, I'm not good with it. Like Honolulu or something like that. So it's going to try to, it's basically going to use this framework to try to determine what is the word you're trying to say, right? And then the computer can go look up this word and do a search or something, right? So that's the type of application these sort of hidden Markov models. Oopsie. Okay, well, I don't know, it's lost connection. So that's the type of applications these sort of hidden Markov models can be useful. Okay, so any questions?
I'm fine.
Okay. Okay, so then we'll end class here. So let me know if when you try to implement the common filter, I mean, not the particle filter, let me know if you have any questions. So again, you should answer the first 4 questions before trying to implement the code. Okay, then I'll talk to you guys next week then.